we're going to find the maximum and minimum values of the given objective function on the indicated feasible region. The objective function here is m. It is a function of both x and y. If we were to graph the function, it would be a flat surface in space, and we can think about it like the surface of a coffee table, balanced on the legs, which are at the positions of the vertices in the feasible regions. The length of the legs corresponds to the value of m at that particular ordered pair x, y. So looking at this example, we have the vertices of the feasible region as 0, 3, 0, 6, and 4, 0. We use these values to calculate the maximum and minimum of the function m. So for 0, 3, we would have 350 minus 0 minus 3, or 347. For 0, 6, we'd have 350 minus 0 minus 6, or 344. And for 4, 0, we'd have 350 minus 4 minus 0, which is 346. So the maximum of m occurs at 0, 3. The minimum of m occurs at 0, 6. The maximum value of m is 347. The minimum value is 344. We have a second example in this video. This time our objective function is called p. We're going to maximize and minimize p based on the feasible region, which is defined algebraically as x greater than or equal to 0, y greater than or equal to 0, 2x plus y less than or equal to 10, and 2x plus 4y less than or equal to 36. So first of all, I'm going to rewrite the last two constraints so that the y is isolated. I'm going to get y is less than or equal to negative 2x plus 10, and y is less than or equal to negative 1/2 x. Because I'm going to divide the negative 2 by 4 and plus 9 when I divide by 4. So in that last step, first of all, I got 4y equals negative 2x plus 36, and I divided by 4. So let's look at the feasible region then. It includes the positive x and y axes, y less than or equal to negative 2x plus 10. So let's put 10 up here. And it has slope negative 1/2. I'm sorry, slope negative 2. And so it would look like that, where this would be 0, 5, 5, 0. That will be the x-intercept. Right here, 5, 0. All right. And the last constraint has y-intercept 0, 9. And slope negative 1/2. So it is going to have a y-intercept, which is an x-intercept, which is actually positive 18. And this is not to scale, but this would be the point 18, 0. And so it's everything below each of these lines as well. So below and below. And so I believe the feasible region then comes out to be this one right there. And 3 of the vertices are 0, 0, 0, 9, and 5, 0. We don't yet have the point of intersection of the last 2 constraints. But if I set the negative 2x plus 10 equal to the negative 1/2 x plus 9, I'll get 3/2 x equals 1, or x equals 2/3. And when x equals 2/3, we can get that y equals negative 2 times 2/3 plus 10, which is negative 4/3 plus 30/3, or 26/3, which is 8 2/3. So 2/3 and 8 2/3. Probably just report that as 26/3. So to find the maximum and minimum this time, we are going to use the 4 points 0, 0, 0, 9, 23, 26/3, and 5, 0. And we're going to evaluate the function p. So at 0, 0, we get 130 minus 0 plus 0, which is 130. At 0, 9, we get 130 minus 0 plus 27, which is 157. At 2/3, 26/3, we get 130 minus 2/3 plus 3 times 26/3, which would be plus 27. 6. So we'd have 156 minus 2/3, which is 155 1/3. And for 50, we'd have 130 minus 5 plus 0, or 125. So our maximum value is 157. Our minimum value is 125. So filling that into the answer, 157 and 125.